Welcome to High Tech Heroes, the program that takes you behind the scenes of today's high-tech industries, where you can meet the people and examine the ideas creating tomorrow's technology. And now, coming to you from the studios of Foothill College, high atop the mountains overlooking Silicon Valley, here's your host, Sherwin Gooch.
Hello, I'm Sherwin Gooch. Welcome to our program. My guest this week is Hud Nordin, a computer specialist and video artist.
Hey.
And I guess we'll find out a little bit more about you. Where did you go to school, Hud?
Well, I'm from Minneapolis, went to the University of Minnesota.
Mm-hmm. What did you study there?
Computer science, of course.
Computer science, of course. Well, I guess it's a famous school. That's Seymour Cray's alma mater, I guess.
Sure is.
Mm-hmm. So what did you do in technology? What was your big project?
Well, the first thing I really worked on that was important after I left Control Data was a statewide educational network called the Minnesota Educational Computing Consortium. It was a sort of quasi-state agency that was responsible for educational computing for all grade levels, from kindergarten up to state colleges and University of Minnesota.
And that must have been a large number of computer terminals to run.
Yeah, there was probably 100,000 clients. Those are students, and certainly thousands of terminals, mostly TTYs. Those were the good old days.
TTY meaning teletypes?
Teletypes, the old...
And those were scattered all over the state of Minnesota?
That's right. And some as many as 350, 400 miles away from the Twin Cities where the central computer was housed.
That's quite a telecommunications problem.
Well, it is, and it was quite expensive, too. The state legislature, in their wisdom, saw fit to make equal access for students so that Twin Cities students weren't favored, and they funded about $4 million a year to pay for telecom.
So did you have a large number of computers to support this?
We had one, yeah.
One?
Yeah, Control Data Cyber 73.
Uh-huh. And is that a very large computer then, or is that...
Well, large in physical size. Actually, its equivalent today would be a high-end desktop computer.
Really?
Yeah.
So, I mean, how much memory did this machine have?
Well, I think 256K, although I don't remember for sure. They didn't have very much in those days, although those are 60-bit words instead of the normal 8-bit.
So that would be about 2 megabytes, roughly?
You compute it, yeah. Not very much.
And how much mass storage?
Quite a bit. Counting in my mind, I see about 10, 12 disk drives, each with probably 100 megabytes. So there was quite a bit of mass storage. I have an example of the technology we used in those days. And this is a disk platter that I stole from the machine I was working on. It was an old machine that was finally decommissioned. And I obtained this disk drive just as a little souvenir. It held about a megabyte.
Mm-hmm. This is 1 megabyte is
That's
all.
right. Mm-hmm. Today, a similar size, or this size, would hold the same amount of storage.
And what is that you're holding?
This is the floppy disk from a 3.5-inch disk drive.
Just a regular disk,
right?
That I have in my pocket.
Broke one open and split this out. Just the contrast.
Okay. And did you also bring some memory?
Yeah, I figured about a megabit would do.
A megabit.
This is a core plane. People have heard of core. This is it. These little black spots you probably can't really pick up on TV are individual donuts of ferrite material. The core plane from an ECS unit, extended core storage, and this is about approximately 1 million bits of information.
Amazing. And this is a chip of today, which would hold just about the same amount of information.
Right.
So it's a little bit smaller.
Well, 20 years is a long time, I guess.
20 years, yeah.
Let me get this out of the way.
So what did you do after you left Minnesota?
Well, I think I was suffering from a bit of burnout and had to get away from computing for a while, so I traveled for a year. Spent some time mostly in Taiwan.
And did you see any of the Taiwan manufacturing there? Or?
Yeah, a little bit. Mostly I was interested in the educational facilities. I was contemplating teaching there and checked out their computing facilities, which were some years back from ours at the time. But
And so what did you do next? technologically after Taiwan?
Right. After a year off, I wanted to compute again, and I joined Atari.
Atari. This is, I guess, the old pre-Tremel Atari?
Right. I spent approximately the last year of Atari's downhill slide there. It was not a pleasant time.
That must have been quite interesting. Well, what did you get accomplished while you were there?
Well, I did work on their disk operating system, their file system, a new version of that, and also really the last person to touch the operating system.
So you did the operating system for, now these are game machines or the computers?
These are the home computers, the 400, 800, 1200 XL line, and also some machines that never saw the light of day, the 1400 and 1450.
Oh, well,
they were hot machines.
Quite a few machines. What did you do after Atari went down the big slide?
Yeah, Atari was a real problem and pretty depressing, but many friends of mine were at Atari to try to do a national network, Atari Central we were going to call it, that would have provided electronic mail, multiplayer games, similar sort of thing, software downloading that you could do with a large central system. And it seemed like Atari was the ideal place to do it because Atari was owned at that time by Warner Communications, and Warner was heavily into cable TV at the time. We felt that cable was an ideal distribution media for that.
Well, and so did you build Atari Central?
No, it was never funded. We had a lot of pleasant dreams about it, though.
Oh, that's really sad.
Yeah.
Did you find somebody else who was working on a gigantic network like MEC or Atari Central?
Yeah, fortunately I did. It was a dream I've always had. And Paul Barron of Packet Cable. Paul Barron is the inventor of packet switching, although he didn't name it, but he invented the concept.
That's a pretty fundamental telecommunications idea.
And he's applied it in a lot of companies that he's founded, and Packet Cable was one of them. It later became known as Packet Technologies, but their goal was to do two-way interactive cable TV, where you could sit at home. Besides getting your normal cable services, you could get data services. You could have bank at home, shop at home, multiplayer games again, electronic mail, anything you can do with a computer.
Well, that sounds
really.
like a dream. I'd like to have that in my home. What happened?
It was an amazing system. About 100 people built it, and it was working.
And this worked over cable television,
right.
So it had to work outdoors in the heat and the cold.
Extreme environments. And it was really slick. You could come into an absolutely dark home and pick up your remote control and hit 3 keys, and you could be, for instance, in inside CompuServe or Dow Jones service or any of the other large information providers, besides watching television, of course.
Well, that sounds great to me. It sounds like what the future should be.
Well, I wish you would have bought one at the time. We had a problem selling them. It was a very conservative industry, and hard to convince a cable operator who only knows about HBO and Showtime that electronic mail was something that was going to make you money.
So can I buy one of these now?
No, the company failed.
Oh, I'm sorry to hear that.
Yeah.
So where did you go after that company failed?
Well, I thought I'd take it easy for a bit, and did, but eventually wound up at Apple Computer.
Uh-huh. And can you tell us what you're doing at Apple? Or?
Well, I can't tell you very much. I work for the communications product development department. It's a long name. And much of what we're doing is proprietary, but I guess I can say that we are involved with connecting Macintoshes with other existing networks out there. For instance, IBM.
Oh, okay. Well, we wouldn't want to pry into that. So, do you have any hobbies?
Well, it seems like most of my hobbies are visually oriented. For instance, painting, woodworking, bonsai, photography. I brought an example of a painting with me here.
Yes, I couldn't help but notice it.
You might enjoy seeing it. Well, it ties into what I'm currently doing, and I call that video synthesis.
Do you have any more examples? Or?
Well, I have examples of video synthesis. The reason I got into this video synthesis, this computing of artworks, was that a painting like this really takes a long time to do. It's just a mess with the wet paint and the time you have to invest. Although the effect is nice to have an artifact that you can actually touch and see detail on it, the hand crafting. But I decided to try to use a computer to do something similar.
Were you able to do that?
Take a look at this.
Oh, well, this is very nice.
I combined my hobby of photography to capture that particular object, but it's just a shot of a screen, of a computer screen, and I wrote a program that helps me generate images like this. My art was always fairly mathematical, geometric in nature, and seemed like a computer was an ideal thing to do.
So we have more examples.
I have plenty of examples here.
Oh, this is beautiful here. I really like this one.
Yeah. Actually, I wish I could take credit for that one. The computer has a free running mode in it where it randomly picks parameters and generates the video all by itself. And that particular one was done in that style.
You have...
here's another one.
Yeah, I think this is all... Now, I understand you brought some equipment along that you can show us.
Yes, I did.
Well, let's go see it.
Yeah, it's a kinetic art, so really the still photos don't do it justice. I want you to see it in motion, actually, and I'd like to start out with a couple of just examples before I try to explain how this works. Maybe examples similar to those still pictures, but showing the motion that you'll find interesting. Now, the setup I have here is a Macintosh 2 computer with the monitor that comes with it, keyboard, mouse, standard input devices. And I'm also hooked up a board that sits in the Mac 2 that is manufactured by Computer Friends, although several people are making them now, that will generate TV signals. And I thought that would really help this.
Are you saying that this is a video synthesizer? This is your video synthesizer here?
This is it.
It looks a lot like a regular computer.
This is actually more than I need. It's a regular computer.
But except that it has this board in it, which allows you to output regular television signals.
Exactly. The board really helps in this situation where we're in a studio. I've also used it to generate videotapes of these things because I really did want to catch the movement of it. So I'll start the program here, and there's an example. Now what I want to do is switch over to generate a TV signal.
That's very beautiful.
Thank you. And a little bit of clicking. And
now this turns, I guess, that turns the computer into the television.
Right. So now your viewers can hopefully see that image a little bit better.
Now you say this is a video synthesizer. Is that anything like an audio synthesizer or a music synthesizer?
It's really very similar. That's where I got the idea for the name, comparing it to an audio synthesizer. Audio synthesizer, of course, is what people are familiar with musicians using these days. It generates the sounds algorithmically or mathematically. The musicians don't always know it, but there's mathematics and algorithms behind what they're doing, and it's producing pretty sounds. Same thing's happening here. We have mathematics, algorithms behind it, and it produces pretty video.
Well, could you show some more examples?
Oh, sure can. Let me close this, and this will automatically bring up another window that has...
So is it computing this quickly?
Here.
That's very fast.
I wish it was. No, it still takes 2 or 3 minutes to compute one of these objects. It's fast enough to be fun, where you can iterate and see the results of your work and decide it's not what you want and then try again. But these images are actually stored on a disk file or disk files. Each one's an individual file. And I can call them up to save time in computing them.
I see. Well, it's good to save time, but could you tell us a little bit about how you put one of these together? I really don't understand the process yet.
Well, let's start with a simple equation, because they're all based on equations or functions of really 2 variables. And what I'm doing is, this will require a little hand waving, I think, to communicate. But I have a function in 3 space, in 3 dimensions. It's a function of 2 variables. Okay, so we have the x, y plane.
So this would be x.
Something running through space. Right, x and y. Okay. Actually, the 0, 0 point for x, y is right in the middle of the screen in this case, although that's flexibly placed. You can put it anywhere you want to. But I have a function that goes through space. Now, similar to what cartographers do, map makers do, to put 3-dimensional information like the height of mountains on a 2-dimensional surface, a piece of paper, I'm doing the same thing. I'm mapping this 3 space onto the screen by representing the height above the plane, above the XY plane, as a color. So, for instance, in this, perhaps red is 0, and yellow is 64,
what is
and
the
green
equation
is
here?
128. Well, this is a very simple equation, z equals x. So you would expect that the colors would change with x.
This is just
so
increasing out like
right.
this.
So yeah, what you're really looking at is a plane that just goes through the y-axis.
I see that it's red here, and it turns, I guess, green is higher than, or yellow is higher, and then green is higher, blue is higher,
right.
or a larger value of the function. It turns red again here.
Well, I have to reuse the colors. I have 256 colors to work with. It's known as a palette. This computer is actually capable of generating 16 million some colors with the right equipment, but I am restricted to less than that. And I'm showing 256 of those 16 million possible colors at one time on the screen.
Okay, I'm not sure I exactly understand this.
Well, for instance, red is representing both 0 and 256 and 512, multiples of...
So you have 256 colors at a time.
Right.
But you can choose out of 16 million colors?
Right. And for instance, if I tire of those colors, I can pick, for instance, some blue-green shades. Here, white is representing 0, and black is representing 255, and green somewhere in the middle.
Now, how did you put together the complex figure that we saw?
Well,
or something like that. How do you put together these more complex artworks?
Let me bring up something just slightly more complex. This is the square root of x squared plus y squared, which is basically you're looking down into a cone. And first of all, I want to introduce this concept of animation. Now, instead of actually selecting a whole different set of 256 colors, I can just shift that set of colors so that at one moment white may represent 0, the next instant it represents 1, and shortly thereafter it represents 2.
So that would be like, here is white, and then white is out here representing new numbers.
Exactly.
Okay, I understand now.
So getting that movement is very easily accomplished. I don't have to keep recomputing circles. I'm just changing a little bit of table information.
So you're actually computing a new, or by special purpose computation, a new picture every 60th of a second,
right.
30th of a second here.
Right. It does look different, but there's far less computation. Normally a screen like this would take a minute to fill, and I can change it very quickly.
And evidently you can speed that up.
That's right. I was just playing with the speed controls here.
Okay.
Everybody likes it a little bit different.
I kind of like that.
Okay. Well, just to make things a little more complicated and to get an more interesting figure to look at. This is that same figure you just saw with the arctan of y over x added to it. For those of you familiar with polar coordinates, we're looking at r plus theta, very simply, but it's a really pretty object, I think.
It looks like a pinwheel.
Exactly. Would probably behave like such in the wind, too. Let me change the colors a little bit. See, it's real easy to get a different effect in the colors.
But it's still a pinwheel.
Right.
With many, many blades.
Right. This particular set of colors itself seems to show some three-dimensional effect just because of the shading. Kind of look like tubes. But it's still just 256 different colors. Well, some of the colors are the same, actually. We have some blacks in there that are several of the 256 colors are black.
It's not good.
Let me take it a step further and take that object and add some special effects to it.
Oh, my.
So this should look just like the thing you saw, except it's a little bit smaller, and there's a lot more of them.
There are a lot of them. Looks like about 16 by 16 or so.
Yeah. Now, if I could find the mouse. There it is. It's a problem. I actually have two video boards in here, and sometimes the mouse wanders down into the, or the cursor wanders down into the other video board, so I have trouble seeing it. Okay, this is how I add special effects to it. For instance, the size of the pinwheel is affected by these two parameters. I can stretch it in either direction or squeeze it in either direction. And this parameter changes the...
Now, these pictures are actually showing that. This
yeah, I tried to do a...
and this is squeezed.
I tried to do a before and after on these. So, for instance, in this case, you take a small square around the center and repeat it over and over.
That's what we just saw.
Right.
All
so
these
you saw
postage stamps.
multiple copies of the same thing. And all of these effects have a parameter related to them. For instance, for this tiling option, the postage stamp, as you called it, this number reflects the size of the square you're using.
Okay, I think I understand now when you were talking about it being like a music synthesizer, because this is the same thing they used to do in the early days of music synthesis. You'd hook together many modules
right.
and process the signal, and it looks like you can hook together
Yeah, they call that chaining, I think.
chaining the modules. So you can chain your functions or your modules
Right,
here.
so, you know, if I want to take one particular effect and then add another effect, just select them off that.
And that's the fundamental activity of video synthesis then?
That's right, just put the pieces together and you get some new video. Okay, well, next we can look at this same function with some added special effects. And close that.
Okay, so this is like running it through another module of synthesis?
Several more, as a matter of fact. This is mapping it onto a sphere, so you get that spherical look. I've added some random noise to it, so there's a sort of a texture to it, and...
Oh yes, I can just barely see the texture.
Well, it might be hard to see on TV. It's easier to see on a monitor. Things look a little fuzzy anyway. And also I've done some scaling on it, which mathematically is flattening out the equation. In the case of the artwork, it tends to spread things out a little bit so that the props of the pinwheel look a little bit wider.
Okay, and do we have more?
Well, I wanted to show you a little trick I developed. Somewhere along the line I decided that what I wanted to see was two functions at the same time. One is never enough. And one way you can do that is by just opening a second window, of course. And this is how fast it fills a window. That is our old friend z equals x for a function.
Now that's amazing. Are you having to do twice as much computing now to do two of these video synthesis artworks at once?
Well, no. Actually, this kind of comes for free. These windows are just filled. That's where the real computing takes place, as it fills the window with the object. But the animation you get, again, is done by the color palette trick to move the colors around.
It's rotating the indexes.
Right, the set of colors.
Lookup table, yes.
Exactly.
Okay.
But I wanted to show you anyway what a window looked like, and that you could have more than one and play with them like regular Macintosh windows. That's a bit of a cheat, though, for getting two things at once. What I really had in mind was something that I call multiplexing. And let me show you an example of it. I think I chose the word multiplexing just from my data communications background.
Yes, multiplexing means that you take one signal and then another and alternate them?
Right. Yeah.
One of n.
Getting many into one, or demultiplexing, getting many out of one.
Now, I only see one signal here.
You only see one signal, but there's actually two functions going on. If you can see the spokes of the wheel.
Yes, I can see the spokes
And
here.
also the circles that are expanding from the center.
Yes, expanding concentric circles.
Okay, so those are the two functions that are involved. One is the square root of x squared plus y squared, which you saw before. And the other one is arctan of y over x, which is just the spinning spokes, or the spinning wheel. So these, in effect, you're looking at two functions at the same time. The screen is filled 50% with one and 50% with the other. The first way I thought of doing this was to just regularly stop at each pixel and either use one function or the other. A pixel being a picture element, the smallest units on the screen, what I'm really painting with. So it was either one function or the other, very regularly. Like the odd ones would be one function, and the even numbered pixels
You're saying
would
every
be
other
the other function.
every other dot on the screen would be either one picture or another,
Right.
like a double exposure.
Right, just like a double exposure. That's very much what it would look like.
Okay.
Very quickly, I decided there were other ways to do 50% one function and 50% the other. And it occurred to me that I could use a flip of the coin at each decision point to decide whether to pick one function or the other.
So this is really random.
This is an example. I call it stochastic multiplexing, just to be fancy, or random multiplexing. It has an effect of giving a nice texture to the
Yes,
to
it
the
looks
object.
like a frosted glass window.
Yeah, I think so. Let me.
I've never heard of this stochastic multiplexing before. It's random multiplexing. It's a new idea.
Right, you're sort of getting two things for the price of one. I guess in the case of the brain looking at an artwork, you fill in the missing details, but you could just as well not fill in missing details, have everything there, and just take twice as long to see it. Let's look at some other versions of this. I can pick other palettes that give it a completely different look. Let me try something simple.
Kind of an aquamarine look there.
No, I call that the water palette.
Oh.
I based it on a swimming pool, I think I saw once. There's simple palette going from white to blue to black. You could probably see better what the actual functions are. The expanding circles and the
It looks entirely
wheel.
different.
Right. Now, some people like it to spin the other direction, and I can do that. There's a control for saying which direction things are moving.
Yes.
And let me go back to this original palette, because the effect gets even better. So now it's spinning. I guess the wheels are spinning clockwise and things are retreating. Now, actually, I like the expanding view of things better, where it looks, I don't know, just more positive to have things expanding rather than shrinking. But you can have both at the same time. I call this sinusoidal animation. Instead of just simply rotating the set of colors, I'm rapidly spinning them one direction, then slowing down and stopping and spinning them the other direction.
Yes, this reminds me of a washing machine.
Well, yeah, I think this could...
something hanging and twisting.
I think for those people who like to
Back
sit
and forth.
at the laundromat and watch their laundry go around, I think this could be a cheap alternative. If it doesn't make them seasick. Let me show you another function here.
Okay.
Something that I just picked as being more artistic. This again involves multiplexing. In this case, this is the regular multiplexing I spoke of earlier, whereby I'm just picking every other pixel as one function or the other. The two functions I use here happen to be almost the same function.
And which are they? Can you outline them?
Well, one has petals going, look at the flower there. There are a set of petals going in clockwise spirals and another set of petals going counterclockwise.
Oh, so these are two spirals that go different directions,
Yeah.
but
I can
multiplexed together.
Right, I can stop the motion briefly.
I see, yes,
so
I
you
see
can see, those are the two functions. One is a clockwise spiral and the other is a counterclockwise spiral. They're really the same function except mirror images of each other. And I put them on the screen at the same time.
And how long does it take to compute a function or a set of two functions like this?
Well, you asked me at the right time. This particular function is the one that I believe takes the longest to compute. It is rather intensive in trigonometry. It's based on a Rose function, so-called, but it's got an added effect whereby, based on the distance from the center, you rotate the object one direction. So there's a lot of trigonometry going on. This one takes a few minutes to fill a
But
screen
generally
with.
it takes about a minute or so.
A minute or two, yeah.
Okay, well, I have an idea. Hey, Mr. Bill, that's our director, Bill Weigel. Do you think you could do a max headroom effect with us? Do you have a good background that we could use for that?
Let's try this one.
Yeah, well, thank you very much for being with us this week, Hud. And I hope everybody will watch for the next episode of High Tech Heroes. We have planned another guest by the name of Simon Field, a technologist from the area, who has begun to study electric fish. He found that there were a number of small fish that you could have in your own aquarium or fish bowl, and that they emit electrical signals, strong enough to shock you, actually. And these fish use these signals to communicate, and also, at least he believes that they use them to communicate and also to locate with, like radar, and I guess analogous to what dolphins do in echolocation. So I think that's very interesting, and that should be a very interesting show, so be sure to watch for the next episode of High Tech Heroes, when we'll show you electric fish. And thanks again for being here on the show,
pleasure.
Mr. Nordin, and I really like this. I'd like to have one myself.
Let me show you another function.
Sure, I'd love to. I mean,
I have plenty of these things.
I can play with this all day.
Thank you for joining us this week on Foothill Focus for the pilot episode of High Tech Heroes. Be sure to tune in again next week when we will be bringing you more entertaining information about people and activities at Foothill College. And now, this is your announcer, R. Conrad Griffin, wishing you the best of luck and a pleasant spring.